Well, howdy. Let's go mess with some limits. We're gonna walk ourselves right into the idea of a one-sided limit. Because here it is. I'll tell you the game. I'm gonna ruin the secret. The limit from the left needs to be equal to the limit from the right for the actual limit to exist. What the hell does that even mean? You're just saying words. Yeah, but that's the secret. That's the big thing. That's the one thing I would hope that we could catch from this whole piece. That the limit from the left, and when I'm saying from the left, I mean x values that are smaller than. Shit, let's just get into it. Here's a little graph. I don't know, it's just something randomly, just kind of, I don't know, put a little flare, put some loops in there, I don't know, so maybe it's some cubic function. Maybe it's a cubic function. I don't know what it is. I just call it y is equal to f of x. Neat. Yeah, it's a graph. What we want to know about it is this. Here's our question. What's the limit as x tends towards 2 of our f of x? Well, there's our f of x. We're like, well, what happens as our x value gets close to our 2? What's the y value? That's what it's asking. I'm just saying, hey, what's the frickin' y value when your x values get really, really close to 2? So you're like, I don't know, what, like -1? Right? All right, cool. And you're like, well, shit. It's equal to -1. Woo! And we can look at it. And what's nice is if it's a continuous function like what I just drew, that's always going to be true. It's going to be equal to the functional value just by plugging the shit in. Just plugging the value in and just go and see where it's at. It's not always going to be the case, though. You'll see it in a minute. So I want to start with something simple so we can start to talk about there's another type of notation. Now let's write this notation. I'm going to write down here, and this is introducing from the left. Now I'm giving you an example. I'm not giving you the definition yet. I figured let's make sure we understand what the hell's going on before I start getting crazy with all the words like last time. So we'll say the limit as x tends towards 2, but we're going to write it differently if we're coming in from the left. We think about from the left being that's over here. The left, and that's in the negative, so that's what we're going to write. We're going to I'll put it in pink so you can see it. We're going to put a little negative sign there, just saying we're coming in from the left of our function, and we want to see what's that equal to. So let's take a little ride. Let's go take a look. So we're going to jump on the train. We'll just get on this thing. Now, don't think up and down. F that. All right. When we're talking about left and right. So while I am moving up, I'm just thinking we're moving from the left. And we're going to go until we start pointing at whatever it is. We're like, oh, there it is. We're pointing at that from the left. Now, what's that height? Oh, shit, it's -1. It's equal to -1. It's the same thing as what was up here. Why are we even doing this? Because it's a point I'm trying to get to. Okay. And then we also have, well, shit, if there's something from the left, you're going to believe me, there might be something from the right. So we say from the right, we say the limit is our x is tending towards 2. And let's put that thing all big and in pink again. We're going to say, but now we're going to put a plus sign in there, saying we're coming from the positive values of x, or from the right of our function here. And we look and we're like, well, let's take another ride. We're going to come from the right. Here we go. And it comes in, and holy shit, they're pointing to the same spot because they have the same height. And really what's going on here is our first theorem. If the limit from the left equals the limit from the right, if the limit from the left equals the limit from the right, well, then that is also the same thing as the actual limit. We don't really give a crap about a limit from the left, limit from the right. We just care about the damn limit that's up here. But sometimes we got to do a little bit of work of understanding that it needs to come from the left and the right to equal the same number. Okay. All right, let's go back. Let's go talk to old Uncle Heaviside here. I did not spell Heaviside wrong. It's a gentleman, it's a British gentleman. I think he's an electrical engineer in the 1800s or something. Or he was born in the I don't know. And we got a little function here, and what's beautiful for us is it's great for lefts and rights to show you. So we want to look at our Heaviside function. And if you're like me, oh man, piecewise functions like this, I hated them. eat them. Oh man, drive me nuts. But it's two different conditions. And the Heaviside function, all it is turning a light switch on. You know this function already, which is basically saying, think about zero is off. When the height is zero, this is the heights, 0 and 1. Those are the heights. 1 is up there, 0 is at that. Heights. Those are your y values. So the light switch is off before you turn it on. So it says before you touch it. So here's the game. Turn the lights on. Okay, now go up to your light switch. Now time hasn't started yet. Now think about it. That when you touch the light switch, it's like you're hitting the stopwatch and it's starting. And saying, now the light's on. Once time starts greater than or equal to 0, now all of a sudden that shit's on. That's the Heaviside function. Cool. But our question is, what is the limit as our t value? So I'm not using x this time because time works so much better for this. What are our, I'm using, as our t gets closer and closer to 0, so there's t equals 0, right down here. That's t equals 0. We want to know what's the limit. But what we can tell for absolute certainty is that the limit coming from the left is not equal to the limit coming from the right. Now, if the limit from the left is not equal to the limit from the right, then our actual limit does not exist. Because the limit as t tends towards 0, let's start from the left-hand side. The left-hand side is over here. That's back over here. And that's pointing towards the height, not the x-value, the height of it. And that's equal to 0. And then our limit from the right, as t goes to 0 from the positive side of our Heaviside function. And what's happening here, we're like, there it goes. From the right, we're coming in here, and we're pointing there. And they're not pointing to the same heights. They're pointing to two separate heights. 0 does not equal 1. Therefore, the limit as t tends towards 0 of h of t does not exist. This is what we wanted to get to. This is the point. That's the point. So, if the limit from the left does not equal the limit from the right, then the actual limit does not exist. And again, we don't give a shit about the limit from the left and the limit from the right. The only reason we're talking about it is because if those two conditions are met, shit, are actually limits then. Let's get into our definitions. We got to do it. Here it is. It's the big thing. If you catch nothing else, the limit of the function is equal to L. Only. We write if and only if here. We'll talk a little bit about this in a second. If and only if. It's like an equal sign. Both of these conditions are met. The limit from the left also equals L, and the limit from the right also equals L. So they all have the same thing. They're all going to L. They're all going to L. They all go to the same spot. So if the left and the right, these two things are done, that will imply that this one's true. And if this one's true, we know that 1 and 2 are true. Both of those two. Okay? If and only if is like a two-way street. It's an implication that goes both ways. Because it's not always true. If it's raining, there are clouds, right? It's not necessarily true if there's clouds, it's raining, right? If and only if. But our big game, the big thing we wanted to see, that's our big thing. If the limit from the left equals the limit from the right, then the limit actually exists and it's the same damn number. But if this is not true, it implies that our limit does not exist. I know it's a lot. You'll get practice through your homework, though. You'll catch it. There's our little definition. You're gonna need this. Get that shit out to do your homework. It's gonna ask you to play that same game with the arbitrarily close to and the sufficiently close to. This bullshit here. F of x arbitrarily close to whatever that value is, and then our x to be sufficiently close to whatever the heck that a value is when x is less than a. Of course, we got one from the right too, but I'm not popping that shit up. I mean, here you go. Here's your. I'm not writing all the freaking words in there or anything. You know what I mean? But that's how we write it from the right, and we say arbitrarily close and sufficiently close to x is more than a. It'd be on the other side. So there's the beginning. There's some shit.